So, hello everyone. Can you hear me?
Yes, sir.
Yes, sir.
Okay. So, I'll just share the link to the YouTube streaming and also link to today's where we'll be uploading the notes. So can anyone of you confirm that the streaming is audible? So I have sent the link to the chat in the chat. If the streaming is audible, because there was a audio issue once. Yeah, okay. It's clear, right? It's loud. Yeah. Yeah. Let's start. So today we'll be introducing the basics of the foundation for doing neural networks, because next week we'll be doing neural networks. We'll be doing logistic regression. That's the basics. That can be thought of a single neuron in a neural network. Anyways, we'll be doing this logistic regression for some time, because we have already looked into it, and most TAs will do that as well. But the most important thing that we'll be doing today is we'll be doing SVMs. So we'll be doing all the we'll also code an SVM from scratch without using any library as such. So before going on to what is logistic regression, so today's class will be mainly dealing with classification problems. So what is a classification problem? So given your data, you will be given x comma y as your data, where y will be labels, say from n labels between 1 to n. So that we have n labels from 1 through n. So the task of the classifier is, we have already seen this in decision trees and Bayesian learning, but the task of the classifier is to input x and predict y hat belongs to 1 to n. So which of the class does this current sample belong to? This is the work of the classification problem. So generally today we'll be dealing with binary classification problem. So anyways, if it is more than 2 classes, we can always extend it by using just softmax instead of logistic regression. We'll come to that next week when we do we'll do neural networks. Anyways, so think of this as the points in your plane, and you're told to find a classifier. So one thing you could do is you can draw a line like this to separate these examples from these. So this is basically the idea of a general classifier. So we need to today we'll be only dealing with linear classifiers. Linear classifiers as in, we will try to have a linear decision boundary. Or an hyperplane separating the classes. In 2D, that's nothing but a line. So you need to fit a line so that you distinguish on one side of the line. So if you remember your class 11 maths, so if this is the equation of the line L of x, So Lx, a point this side of your line x1 hat, if this is less than 0, then x hat this side of this line will be greater than 0. So this is clearly, if it is less than 0, you'll be classifying it as a positive or a positive example, or and vice versa for the other case. So is the broad idea about a classification problem clear, or if anyone has a doubt, you can ask, or we can proceed to the particular algorithm of a logistic regression. Don't think there is a problem regarding this. This was a brief recap. So let's define a function first, and then we'll be coming to what is binary classification problem. You just look at the right side of the page here. So we'll be defining a function. This is known as a sigmoid function as 1 by 1 over e to the power minus x. So if you plot this graph, what will you see? Limit x tends to infinity, sigma x, where does this tend to? It tends to 1 by 1 plus 1, that is 1 plus 0, that is 1. Yeah. And at 0, you can clearly see this half, because x is equal to 0, sigma of half, sigma of 0 is equal to 1 by 1 plus e to the power minus 0, that is half. And similarly for negative infinity, the e to the power minus of minus x is positive, huge number, so that tends to 0. So the graph will be something like this. So you can take the derivative and see that this is will be anyways taking the derivative. It's a continuously increasing function of these characteristics. So why is this function that important? So this is because if we model anything like sigma of x, this will be output. This sigma will output any number in the real number line between 0 and 1. So this sigmoid function can give you a probability distribution for a Bernoulli variable, right? So given an R, it can tell you, so if the x value is greater than 0, so let's dive a bit deeper into this. What does this mean? So sigma x is greater than 0.5 if x is greater than 0, right? And sigma x is less than 0.5 if x is less than 0. You can clearly see, I explain how the graph is drawn. It's 0.5, this is 1. So if any value x is greater than 0, it's more than 0.5, less than 0, it's less than 0.5. So these are the two things. So you can clearly see if we design a classifier such that we predict positive if sigma x is greater than 0.5, that is more than 50% chance of getting it, more than 50% chance of it being the positive class, then we can say this means that x is greater than 0. For a hyperplane to have that property, we need W transpose x plus b is greater than 0. So this is the whole idea of so x will be, so let us write x tilde here. So x tilde is defined as W transpose x plus b, where W times x, this is the data sample. So this is the broad idea. So if this line, when you feed xi, if it is greater than 0, you're giving a positive class. If it is less than 0, you're giving a negative class. Let's consider the derivative. So if this will be required in the next class, so we'll be doing this. So if you take the derivative, you can clearly see, so this is equal to 1 by 1 plus e to the power minus x square, and you take by chain rule, this is e to the power minus x, right? So you take the derivative of the denominator, and then by chain rule take the derivative of e to the power of minus x. So this means that this can be written as e to the power minus x this way, or rather, I'm sorry, this way. So this means that this is 1 by e to the power of minus x minus 1 by e to the power of 1 plus e to the power x square. So this means this is sigma x minus sigma x square. Yeah. Question? This will be required next week. So we just, for yours convenience, we derive it. Yeah.
Once again, this last step, can you explain from the last derivative onwards?
This one, right? Or this one?
No, just, yeah, that one. From that.
So d dx of 1 plus e to the power minus x, right?
Okay.
So what is the derivative of 1 by x? Or x to the power minus 1? That is minus x to the power minus 2, right?
Okay, yeah.
So what does this mean? So this denominator is some function f of x. So this is 1 by 1 plus e to the power minus x, right?
Yes.
Now, what to do? So you know the chain rule. So f of g of x, if you take the derivative of f of x, it is, there's a disturbance in that. Okay, so if you take the derivative of this is nothing but f dash of g of x into g dash of x, right? You take the derivative of the outer function, then you take the derivative of whatever your composition is.
Okay.
So here the outer function is 1 by x, the inner function is 1 plus e to the power minus x. So then you take the derivative of the inner function, you get minus of e to the power minus x. Right? So that's how you get the derivative. Is that okay? Nirmala?
Yes, it's fine.
Yeah.
Yeah,
Yeah.
may I know the reason for taking the derivative? I mean, why we are taking the derivative
It
of
will
that?
be evident after some time. Just I kept it handy, so it will be used next time also, and today also we'll be using. Okay, I just kept it ready, so sometimes we'll be using it in a couple of minutes. So now, did you understand a sigmoid function will actually give you a probability distribution for a Bernoulli random variables where you can output 0 and 1. So sigmoid will give the probability of this being equal to 1, right? So let's write it. So if this is between 0 and 1, the probability of y equal to 1 if y is distributed as a Bernoulli random variable, this is nothing but p. So you can model p as sigmoid of x if you are given x. Is that okay? This is the whole idea of logistic regression. If you have a question, you can ask. So this thing is probability of y is 1 given x and some parameters w is defined as sigmoid of w transpose x plus b. I've written all these in fair. You can just have a look at that. So is this okay? This is how you define this function. So let us say that is mu n. So the probability that the xn probability that xn belongs to yn is mu n. That is given by this sigma function, the sigma of w transpose x plus b. So what we can do is we can do something like this. We can mix both of these. So say that this for a Bernoulli random variable, so yn can take two values, 0 and 1. So here if it is 0, you can clearly see this is 1 minus mu n, and if it is yn is 1, you can clearly see it's mu n. So I'm just writing this is how you define a Bernoulli random variable as. So yn is equal to 1 is mu n and yn is equal to 0 as 1 minus mu n. So if you toss a coin, it's 50-50 both ways. Or if you have a biased coin giving 60% head, so the probability of y equal to 1 or head is equal to say yn, say 0.6, and the other one is 0.4. So this is how we combine both these equations and write it in this form. Is this okay? If anyone has a doubt, you can ask. Or else what we can do is we can do MLE, maximum likelihood estimation, that we did last time. So you must remember that yn, you were giving your given xn, you were trying to predict each yn independently. That's what I did. Last class we had done MLEs in thoroughly, so assuming IID. So and then you take the log likelihood. That is also same, since log is a increasing function. So anyways, this is known as the, so L of W equal to WYI log mu I plus 1 minus yi log 1 minus mu I. This is known as the logistic loss or the cross entropy loss. You put a negative because you are trying to find argmax. Here the objective is to find argmin. So this can be written as this equation here. I'll show you how. So that will be helping you. So here you can see W transpose x plus b is this equation on the right. So given x, the probability mu n can be written as 1 by this equation e to the power of minus x. Here x is W transpose x plus b. So that I just expanded this way. I took the negative, I divided by e to the power minus W transpose x by b throughout and got this. So here you can easily see, so yi log of W e to the power of, so mu I is e to the power of W transpose x plus b plus 1 plus e to the power W transpose x plus b plus 1 minus yi log of 1 minus this, so it's 1 by 1 plus e to the power W transpose x plus b. So you just use property of logarithms. So what will you get? You get W transpose W into W transpose x plus b, and this you will get the subtraction of this term, and this will cancel with this second term. So you in turn end up getting plus log of 1 by e to the power W transpose x plus b. So that is this equation. So this is for a single sample. So this is for n samples. You take the average of all. One sample. Is the logistic loss clear to everyone? How we are trying to do the maximum likelihood estimation? So this is the loss function we want to minimize. So how will you minimize the loss function? That's the question that we'll see now. Is the loss function derivation clear? So this is the very famous cross entropy loss that we'll be using throughout. So I just replaced mu i's with these values and you got this logistic loss. Now, why did I take the derivative, right? That was the question. So in the first tutorial, I had introduced gradient descent. So the idea is to do gradient descent. So logistic loss is a convex function. You have a single optimum point. It's something like this. It looks like this. You have a single optima. So you start off with some x and you take the gradient. So you can travel along the slope of this curve. So by your definition of gradient, x plus h or the derivatives is limit h tends to 0 is defined as f dash s. So we can write f dash x plus h is equal to f of x minus some h prime f dash of x, or rather we can f of x plus h times f dash of x. So this serves as the, So this is one thing. This is how you define gradients. So if this is delta x, this is f dash of x. But here we want to update the value of x itself. So x was initialized here as x1. So how do you update the value? So you can see, I'll show you the geometry. So if I take the slope here, so this theta is your tan theta is equal to dy dx. So initial x was this one, so you want to get this. So this is your, so what can you do? So the perpendicular, what is the difference between these two? This is the difference is f of x plus h minus, rather you can write x minus h. So this is the gradient. You take dy dx in this direction. So you want to change x this way. So x we want to change as x minus some alpha. So you want to move along this base into dy dx. So y is some function of x here. This is what you want to do. So let's see what is this. So this is delta of x that you want to model, and this is delta of y, right? So tan theta can be written as delta y by delta x. So, and what you can do is you can start off with x as this point and you want to travel along x in this direction. So what you can do, you can take a component of the gradient along the base and a component of the gradient along the perpendicular direction. So that's what you can do. So if this is the vector that gives you the gradient u, so you take the gradient along the x direction and you just change the parameters of this function. So basically, so this dy dx gives you this vector along which you change the gradient by the maximum amount. So if you follow this vector by some amount, you will be following this curve and finally ending up on this base. Is this okay? So this is, you will do an iterative solution here. So you'll come down to this base here. Yeah, somebody has a question.
Will you apply this derivative on the sigmoid derivative also to get the...
Yeah, so we'll be doing the derivative on the loss function. So you do in the loss is the function of some parameters. So the loss will decrease, this is the w, so this is the function of w, say. So if you have the derivative is the direction of the tangent. So if you follow the tangent, you can easily get you can trace the curve and finally you can reach this minima. Is the intuition clear?
So that is the reason why the derivative of the sigmoid function is done.
Yeah, that is the importance of the derivative of the sigmoid function. Is that okay? Mr. Shashidhar?
Fine, thank you.
Yeah. So you are trying to do a gradient descent, you update the parameters with respect to these values. So that's why I took the derivative. So I'll calculate the derivatives here. So you clearly can, this function, I'm taking the derivative with the wi. So you can clearly see with wi, if I take the derivative, so you have yi xi minus the sigmoid of this function into xi. So this is why I calculated the gradients. So, and from here what I did is, so this was this function. So if you take the derivative of log with respect to, so you can do both ways by calculating sigmoid, or you can also do the derivative of this. So you get 1 plus e to the power w transpose x plus b, and you have e to the power w transpose x plus b into xi. So this is your sigmoid into some xi. So this is why we did the derivative. So this is the derivative. So it's the summation of yi minus, this is nothing but the sigmoid, that is mu I we defined. So we subtracted mu I into xi. So in a vectorized notation, when you implement it into the computer, you try to represent xi's as columns and take the linear combination of y minus xi's, y minus mu. So this is what will you do. So you update w as w minus some alpha learning rate. The smaller you take learning rate, the lesser noisy it will be. You update this way. Similarly for b, you can see this is clearly you don't have any x term, so it's the sum of these entries. So I'll do an example here and then you can proceed. So think of these 6 points are there on this plane. So you are told to learn a linear classifier to fit these points. So let us initialize w to be 0, 0 and b to be 0. These two initializations let us do. So we will be using these equations that we derived just now, 1 and 2, to update w and b. So let's try. So what are these? Let's take these as 1. That's what I've done. And these as 0 labels. So the gradient was defined as dl dw is x minus, so this is the algorithm that I have. So this is x into mu minus y. So that's what I've done. So mu you can easily calculate by taking the dot product with w transpose x plus b and taking the sigmoid of this. You take the sigmoid of w transpose x plus b and then you can calculate. So for you can see initially I have taken 0, 0 as the weight vector into x if I do, and b is also 0. So if I take mu is all half vector. So it's predicting equal probability for all the 6 points. So this is the value of mu. So mu minus y is half into 1 minus, I have 3 1s and 3 zeros. So that's what I've done here. You can clearly see. So I'll subtract the output and from the actual output and I get this, and then I will multiply x minus y as the equation, as the gradient suggests. I'll take the dot product with the matrix and you can do the maths. You will get this as the gradient. When you get this as the gradient, you take the derivative, you take the so you'll take these, you'll subtract these gradient terms. This is the gradient of the loss function with respect to w, and then you update. So you get something like 0.1 and 0.12. Now immediately you see the vector 0.1 minus 0.1 and 0.2 is something like this. So the plane is something like this. So if you draw this here, it's learned. It has learned to update the plane. Initially the plane was 0, 0. So it did not learn anything. It was something 0, 0 meant. So it was a dot. So now you have a line that is passing through this. And also for b, if you take b, y minus this, so they're plus half and minus half, so it does not change. So is gradient descent clear for logistic regression? This will be the basic that you'll be using for any function. So what we did, we showed that the gradient is the maximum, the direction in which the curve decreases or rather increases in the maximum direction, or minus the gradient is the direction in which the curve decreases in the maximum direction. So you follow the curve along the gradient by taking small steps. So take baby steps and move to the minima. And for that, for logistic regression, we found the derivative of the logistic function or the sigmoid function. And then what we did is, we have this closed form equation. You can try to code this in your computer. So this I'll not show to code, I'll show SVM today. So you just need to define this to functions dl dw, and for every iteration, so for t equal to 1 to say 1000, you will update w as w minus dl dw. I have given you closed form equations, and b as we derived it just now, dl dv. So if you have a question you can ask, or let us go to solve the SVMs. That is the major crux of today's lesson. Yeah.
What is this alpha?
So I told you, right? So you take, so the gradient is a vector. I was giving you this intuition here only. So you have this gradient means it's a vector, right? So you can rescale the vector by how much you want to shift it, right?
But what is the ideal value of that? Ideal
So that
value.
I'll come to that. So what for this you can take small steps or very large steps. In case you take a very large step here, so you will generally overshoot and come here. You may oscillate. So generally for this convex functions you have closed form solutions for alpha, but generally you don't have. You treat it as a hyperparameter.
Okay.
So what does a hyperparameter mean? You try for 0.001 through all the way to 1, say in the log scale. You try 10 values and see which is doing better in the gradient descent.
Okay. Thank you.
That's how you do you get your alpha.
Alpha can also called as a learning rate parameter.
It's a learning rate parameter, or the
range is 0 to 1.
No, that does not mean the range can be 0 to 1. It can be anything. It can be 2 also. It depends upon the
if its value is high, it will shoot up.
Yeah, it depends
and
on
oscillate.
It depends upon the characteristics of the function. So think of a convex function. In convex functions, you may have there are Lipschitz continuity and all these things where you can have values more than 1 or 1. It's possible, but generally you try to tune it between, in a neural network setting, you try to tune it between 10 to the power minus 4 to 0.1 or 0.5ish.
Okay.
Theoretically, for convex functions, you can have closed bounds, but here it's a bit difficult.
Okay.
Because here it's possible. In a logistic regression, you can have bounds. The bounds exist, but when we'll be doing it for general measure, like a neural network, it's not possible to find because those are not convex in nature.
Okay, right. Thank you.
Yeah. So this is a learning rate, or the parameter through which you update your, scale your gradients.
And will these recording sessions will be available after completion of course?
They're all available on YouTube, right? You have all shared the link, so why will it not be available?
Yes, after the completion of course also will be available.
Yeah, of course.
Right. Okay.
We have shared this, so this will not be deleted. So these are the each of these videos will be belonging to the TA that is actually conducting it. So then they'll not be deleted from YouTube. Okay. So the problem with linear regression or logistic regression is like this. So you have something like this, and one term is somewhere here. So this was the initial thing. You may change the curve, or you can say that you can do regularization. Basically regularization is possible, then still you will get this curve. They don't think of this point. So for this linearly separable points, what do you think is the best?
What is regularization?
So I spoke about it 3 times in the first session, second session, third session. So last session also we saw what regularization is. So regularization is, you do not want to bias the weights or make them very high. You want to keep them low, and you actually impose some priors on the weights. So regularization is sort of a high bias condition that you put on your classifier. So leave that. You can follow. You can go through the videos in the last few sessions. You can you'll understand. Also the lecture videos of this course, it discusses regularization.
Okay.
Yeah. So it means that you do not want to have all those functions, but you want to prior yourself on a smaller group of functions. So you tell me, which of these two will you select for your problem? So which of these are best? So logistic regression can choose any of these. So which of these are best? So best, this is what SVM does. It defines something called the best hyperplane using support vectors. So what does using support vectors mean? So you'll have something like this. So we were doing something like this, right? W transpose x plus b greater than 0, you were telling positive. W transpose x plus b less than 0, you are saying negative. So instead of 0, if I put something like this, 1, then I say positive, and W transpose x plus b less than 1, I say negative. But while classifying, I'll be classifying for greater than 0 only, but that's a different story altogether. But I want to impose this constraint. Between 0 and 1, I want no points. This will enable me to do something like this. So if this is the classifier, let me draw it separately. So you have this, two distributions. So this will do something like this. It will select, these are points greater than 1, these are points less than -1. So this creates this margin that is also known as a large margin classifier. So it tries to maximize this margin. This is the entire idea of an SVM. So it tries to separate the distribution in far away. So the hyperplane in a general logistic regression could have been something like this, where still you do well in classification, but still you want, there may be some noise that due to that can come later, or these may be noisy distributions where you do not actually have the actual distribution given to you, because since you are modeling them by data, so you want to make it as robust as possible. So SVM does that. It creates the best plane so that this distribution is separated highly. So let's see how will you solve this. So let's first do the basics of this. So I'll just give you the optimization problem. I'll not go through directly because I thought I'll go through, but you people had a little bit of problem in logistic regression. So let's see. How will you formulate the problem generally? So think of this. So you have some positive samples here. So the SVMs will, positive samples are treated as +1 and negative samples let us treat as -1 instead of 0. Y values. So now you see what is our desire. Our desire is to maximize this distance, right? Sorry for that. So our idea is to maximize this distance. So this is your vector W for this classifier. This classifier you have, this is the plane that you want to point. So tell me, somebody volunteer and tell me, for this x positive, what will be this value?
Greater than equal to 0.
Yeah, that is true, but it is on this line. These are called support vectors. Just to remind you.
Okay.
These are on this line, right? So this line is W transpose x plus b equal to 1.
Okay, greater than equal.
No, it's 1, equal to 1, right?
Okay.
And W transpose x minus b will be equal to?
-1.
Correct. So, and all other points have to be away, not inside. They have to be away from this line. So this is the entire idea. So we will have some vectors that will help us support these two lines. So let us do some basic projection that I have defined for so long In this class I have spoken about it. So you have x plus here, you have x minus here, and you have a vector like this. So you want to find this distance. What is it? How can you find? So if you take the dot product with the unit vector of w with x plus minus x minus, you will get it, right? Hello?
You're talking about perpendicular distance, right?
Correct. Between two lines, the perpendicular distance is what we consider. Otherwise, it does not make sense.
Yeah, okay.
So is this clear? So you have a vector like this. This is the w vector, and positive example here, negative example here. So if you want to see the perpendicular distance between these two, you just take the dot product with the unit vector along the w. That's all. That will give you the, that will take this projection, isn't it? Or you can write this as w by x minus. That's it. So you can clearly see this w transpose x plus minus w transpose x minus. What is this value? W transpose x plus is 1 minus b, right? Don't write it here.
1 minus b, okay.
Yes, and this one is
1 b minus 1. No, minus 1 minus b.
correct. So it is nothing but my b's cancel out. So it is 2 by w. So you want to maximize this, right?
Yes.
So this is equivalent to minimizing
W square.
also square, because this is a itself positive, so square is also square of positive, so it's equivalent. So it will become evident why I took a square of the node.
How did my half came in there?
Just this is for convenience of calculation. So if you add some constants, will the maximum change? So think of this equation, x minus 2 square. If you add c, will the minimum change for this equation?
No, it won't. It
So
won't.
so that it's just for convenience. I'll show you why.
Okay.
So let us just introduce the basics of how you derive the Lagrangian here in this case. I think this is the only thing that will be new in this tutorial, so it will help you in most of your optimization problems. This is the basic of optimization I'll be covering. So see, so if for a constrained optimization problem, so what is the optimization problem here? So you have some constraints also, right? So you see this. So what are the constraints? I forgot to mention. So for y plus, you have to see that w transpose x plus b has to be greater than 1, right? And y minus, this has to be w transpose x minus plus b has to be less than minus 1. Is this clear?
Yes.
So these are the two constraints that you have to introduce. So what we can do is just multiply y plus and y minus itself. So if you multiply, y plus is 1. So on both sides it becomes w transpose x plus b greater than or equal to 1. Is this okay? So if you multiply y itself, which is plus 1 and minus 1 on both sides. So if you multiply minus 1 here, you get w transpose x minus plus b into minus 1. This is easy, greater than or equal to 1, and this can be written as y minus. Is this okay? For now we have been able to integrate both positive and negative examples. This is the beauty of this, taking positive and negative separately. Is this okay? This is the constraint. So you want to minimize this, but you have to abide by this constraint. So you want this. So I think people are having a little bit of a doubt in this multiplication, right? If you don't, if you have, you can ask.
Yes.
So you see, so for y plus w transpose plus x plus, what is this? This is greater than 0, right? Greater than 1, to be clear. That's how we have defined, right? for positive examples, and negative examples W transpose X minus has to be less than -1, right? Now if I multiply, what is Y minus? What is the value of Y minus?
-1.
-1. Value of Y plus?
+1.
+1. So if I multiply -1 to this equation, what will it become? W transpose X minus plus B into -1. Inequality will flip since you are multiplying a negative on both sides, and this one is nothing but Y minus. Is this okay? Y is both of this becoming the same, and here also if you multiply Y plus, this is still the same because it's a positive number. Now is this okay? So how both for Y plus and Y minus, this product will always be greater than 1. Okay? Ramila, you were having a doubt in this. Is this okay? You can ask me if you have a doubt.
Okay, right. I got it, man.
Yes. So if anyone has a doubt, we can ask. Otherwise, we'll come to this. So for coding an SVM, what we need to do is we have a constraint optimization problem. We somehow have to remove it. How to remove it is by a Lagrangian. So given this sort of a function where you have some less than 0 constraint, we don't have these constraints here. You can write a Lagrangian in this form, where you weight each of these functions hi's with some Lagrangian multiplies alpha I, and each of the lj's with some Lagrangian function lj, beta j. So what you can see is this term is less than 0, right? So this Lagrangian term is always less than equal to f of x. Is this argument clear? So if this term is some f of x and this term is less than 0, it's negative. So this right hand side will always be less than equal to f of x, which is just this term. You are adding some negative term with 2f of x, so that is less than your f of x. Is that okay? You add some negatives to the number, it's always less than that number, right? So that's what I've written. So that's how you define. What you do is, in case of an SVM or a dual problem, you want to what you're trying to do is remove these constraints. That's what you're trying to do. So you want to remove this x altogether. For all x, this is true. So if you want to remove x, you do something like this. You remove this x and represent it in terms of alpha and beta.
So please explain Lagrangian again.
Okay, I'll come and explain it here. So the Lagrangian, so you have some function f of x. Let's forget equality constraints now. You want to minimize this, okay? Subject to hi of x is less than 0. So you can represent what, say there are n constraints, 1 to n. So I introduce some multipliers alpha I, I is equal to 1 to n, and I add it with f of x. So what is this? Is greater than 0 or less than 0? Pooja? Each of this term is less than 0 and alpha i's are all greater than 0. For this?
Minor.
Yeah.
What is the literal meaning of Lagrangian?
The Lagrangian operator was defined for a constraint optimization. It's defined after a mathematician, okay? Defined after Lagrange. Lagrange did this way. So you have some constraints. You wanted to you want to remove the constraints in such a way that you can optimize this, which was actually not initially possible. Is that okay? So it's not a meaning is you just add these multipliers and add these constraints. Meaning as in it was defined by the mathematician Lagrange. Is that okay?
So we can say that these are the constraints which are
Exactly.
defined by that mathematician, and we are using that constraints, right?
No, constraints can be anything.
Okay.
These hi's are any constraints. That is, right hand side is less than 0. So like here we have defined these are the constraints. So to remove the constraint for optimization, we need to take some gradient descent term. For removing the constraints, so you will try to add these alpha i's, hi's. So now there is no constraints, right?
So this is to get the maximum hyperplane, right?
So this is trying to whatever you want to do the optimization, say minimization. So there without the constraint you want to do a minimization. That's why you introduce this. So can you see that this thing, this f of x plus this thing is less than 0? Is that evident? If all the alpha i's are greater than 0, then this term is less than 0.
We are minimizing what? Function
F of x.
Function value?
F of x. We are trying to minimize f of x such that these conditions hold always. Within the set of x where these conditions hold, you want to minimize f of x.
Okay.
So that you want to remove this constraint. So it's very difficult to find out in a set, right? You want to do it in gradient descent, you just do it without considering any set. You take the entire number line. So you want to do similar things here. Is that okay?
Okay.
So you want to remove these constraints. How can you say that if it is for every x in a set you can't optimize? It's a continuous, it's infinite elements in a set. You can't optimize. So you want to put this inside this operator. So you want to put this Lagrangian inside this operator. And clearly you can see this term is less than 0. So this means that f of x is greater than this, right? Is that okay? If this is less than 0, you add some negative number to a number. So that is less than the original number. Now you understood, right?
Yes, sir.
So what you try to do next is you try to remove x, marginalize over x. So how do you remove? You find the minimum over x. Even if you find the minimum over x, it's always less than this, holds always, right? This will never hold because this is independent. So minimum is also less than for every x and y. So if you are understanding what I'm saying, so minimum of a function f of x means that this is always less than f of x. Is that okay?
Yes, sir.
Yes, that's what I did. So you removed f of x and you get independent terms of x between alpha and beta. So this is the great idea that we have. So you have this idea that you removed x altogether and you have a optimization problem in terms of the only these constraints now. So now you take the max of this and hope to find that the max of this dual function is equal to f of x. There are some Slater's conditions there. You can, if you want to go through, you can go. For SVM, this max in turn actually turns out to be the minimum of this function. So I have drawn a picture here for the intuition. So let's draw it again. So this was your f of x, right? So this is your f of x. So this, when you add some function, this is f of x plus alpha I hi of x. So in SVM something like this happens. This optimization problem is hard. This is easy. So you solve this and you find the maxima of this. Is this okay? So this is your this point in the SVM. You have minima of f of x is equal to maxima of your dual of f. This is the idea, this is the intuition of a Lagrangian. So Professor Sandeep was asking with the intuition, is this intuition clear? So you have a hard problem to optimize here, you generate another easy problem and maximize over that problem. And they in turn turn out to be same if Slater's condition hold only. You can go through, I have written it down, Slater's condition. There's a bit shortage of time, we need to go through the code also. There you can go through, but if for SVM, Slater's condition holds and these 2 points overlap. Is the intuition clear? Yes, so you in turn solve an easy optimization problem and do it. So now that's what I've done. You can go through the maths here. So I just took that. What will I do? Someone who was following the class will be able to say, what will I do now? How will I remove W from here? Now the question is, what are the original variables? The W and B was the original variable, right? In this equation, this loss function that I defined. So let me just go back. So our objective was to maximize this, right? Or rather minimize this. Do you remember? We were trying to minimize the sum of the weights of the square of weights. Subject to this was holding true, right? I'll just show you how to derive the Lagrangian for SVM. Is this okay? Someone of you, if you have a question, you ask. So this was the objective that I showed. You wanted to find the maximum distance between these two. That turned out to be minimizing this term, and these constraints were there. Is this okay?
Can we always find a point like that where they interact, like in graph, minimum point of the function?
No. You can't. Only if Slater's condition hold. That is, for one point, all these must be less than 0. Since you asked, Pooja, for one point, if h1 of x, h2 of x, and hn of x all must be strictly less than 0. In that case, it will hold. Other cases, it is less than will hold, but not less than equal to. But in SVMs, you can clearly see, you can draw something like this, right? So in this case, for all the points, all the constraints are less than 0. So for this, it is trivially holding. This was the actual thing I wanted to avoid. So anyways, so in this case, what you do is, these are the constraints, this is the optimization problem. So how do you make this like h of I less than 0, Pooja? Or any one of you? So what you do is, take one wi, w transpose x, I plus b less than 0, right? This is a valid constraint for the Lagrangian, right? Or if you have a doubt, you can ask. This is the last important thing that you need to understand before we can go further. After this is just calculation. I just took this to the other side. That's it. To get it in this form, less than 0 form. So now I took some multipliers and added these. That's what I did. Now you take the derivative with respect, since the original equation is respect to w. It's w only. And the final equation we want in terms of these alphas. So you want to marginalize over w and b. That's what I've done. I've written down the math here, you can follow. So I'll put w, I will take the derivative with respect to w and put it to 0 and find the value of w. That turns out to be this. And I'll put the value of b and put it to 0. That turns out to be this. Then you put the value of w and b in this equation, and you in turn get this equation as your optimization problem, where alpha trans g is nothing but, I define g like this, diagonal of y into x transpose. This is a gram matrix. I'll come to why is it called a gram matrix. And this is the dual function that we want to maximize. If you have a doubt, you ask. The algebra you need to go through because we are short on time. We have a few more things to do. Or if you want, I can go through. Should I go through? So I have the calculations here. So what you do is you take the derivative here. So you get 2w. That's what I've written, 2w. That's why somebody was asking why to take half. So when I take the derivative of this with respect to w, I get 2w into half. So this is why I took the half w, for my convenience. And then you take the derivative here and you get the value of w to be alpha n yn xn. Similarly for b, you get alpha n yn. So this is the equation. So forget about the equation, you need to remember these two things. So x tilde is, I generate a matrix where I multiply each row. So this is say x1, x2, xn. I multiply each row with yi's, corresponding yi's. That's what we were doing. So see here, we were multiplying each of these with yi's. That's what I have done. And then I construct this optimization problem. The optimization problem is this. So let me write down fresh. So L of W alpha is alpha transpose 1 minus half alpha transpose G alpha. And you want to maximize this over alpha such that alpha n yn is equal to 0 and alpha greater than 0. This is the basic thing you want to do. This is the optimization problem you want to solve. If you have a question, you ask, or I'll just show you how to do this, or why is this called a gram matrix, or will be. So you can go through the maths rather than the calculations. I've shown you how to do it. If you have a question, you ask me, otherwise I'm going through the next thing. See, there can be points where these are inside these ends. So in that case, you need to introduce some slacks. These are called slacks. So you need to, there's no maths I'll do here. This is for just coding purposes. I'll just introduce this. So these are called the slag variables. So here you remember that this was equal to 1. So I'll show you, think of this line. So you have a point here. So you have this slag variable alpha I. So you have W transpose X plus B is not greater than 1. It's less than 1. So to make it greater than 1, you introduce something like this. W transpose X plus B greater than or equal to 1 minus epsilon beta I, say. So you account for this distance. Whenever, say, the data is not linearly separable, so you will not have a perfect classifier, then you will fail. So that's why you need to introduce this slag variables. So if you introduce this slag variables, what you have is you have the exact equation. You have the exact equation, but the only thing that changes is you have some C that you had defined in this optimization problem. So we would not only try to say, I'll just show here. So the optimization problem I'll try to solve is, can anyone tell me? So one thing is sure, that we will try to minimize this. And can anyone tell me what else should I add here? What else do I want to minimize? Do I want something like this, where the margins are so far away? Do I want something like this? So if I introduce not keep any constraint on the margins, so this will become very far away. So for that, you need to add the slag variables. So if you have large slag variables, you penalize the classifier. The intuition is penalize the classifier for large slag variables. So you don't want large slag variables, have small slag variables, so you add this. So this C is what is exactly added in this equation. So this is added here, I'll show you. So this is what we will be coding. So that's why you introduce. So instead of having unbounded alpha, we'll be having this equation where alpha is bounded by some C. It's now we cannot have any alphas. So I also planned to tell you something about if there are imbalance of classes, what will you do? So let me just try the intuition only. So if you have an imbalance of classes, say one class has only one positive example and all are negative examples. So a classifier will just do fine if it does something like this, right? Just classify something like this. All you classify as positive. So in this case, what you can do is you can differentially weight the slag variables. So how will you differentially weight the slag variables? So in something like this. So penalize the minority class more. So for this, if you have lesser minority class, so that this penalty is very high, so then it will be bound to shift the margin this way. So it will be bound to shift this margin. So that's the reason you penalize. If you have a lower number of samples in a particular class, you penalize it more. So that's what I have done. So C says C positive for all the slag variables in the positive class, and C negative for all the slag variables in the negative class. This is the two things that you want to do. Otherwise, everything is same for even for this thing. So this is just the intuition. This may people may ask most of the times, how will you account for an imbalance of classes? So I'll just show you one thing. Why is this called a gram matrix? And why does this make SVMs very unique? Before we go on to the coding problem, I'll show you this thing. Just see. So the gram matrix we have defined is as X transpose, and our problem is alpha transpose. We have some quadratic in this form. Can you tell me that what is the use of doing this? Why is it very essential, or rather why is it very helpful here? So you can see something like this. So you have alpha transpose X transpose alpha. I'm just putting the value of G here. So what does this mean? So you have X transpose alpha's full transpose and X transpose alpha. This is nothing but X transpose alpha's square. So this is always greater than 0. So this is the help thing. So you have a function like this, L of alpha, alpha transpose 1 minus. So what it tries to do is, it tries to set this to 0, tries to set this parameter to 0. This is the intuition. So I think this is making more of a sense. This is why it's called a gram matrix, or the positive semi-definite matrix. So it means that the sum of squares is always greater than or equal to 0. So that is why, if this term is 0, we would in turn have a softmax or a SVM where we will just have sum of alpha i's. So this is what the objective of the SVM is, to maximize the sum of alpha i's and set this to as close to 0 as possible. SVM tries to set this to as close to 0. So one last question that will help you to understand this is this. Says you have this gram matrix. Read this question carefully. So suppose you have a kernel or a gram matrix defined which has 1, 0 eigenvalue, which means you don't need to think of anything, which means eigenvalue 0 means there is one solution for this. I have defined eigenvalues in the first tutorial. So G alpha equal to lambda alpha is the eigenvalue equation. So if you have 1, 0 eigenvalue, so there is one equation such that for alpha not equal to 0, this is true. G alpha. So that is 0 into alpha. This is equal to 0. So you can clearly see the SVM. What will the SVM try to do? It will try to find this alpha, right? If you have found this alpha, you are done. If you have a doubt, you can ask. If you can find this alpha at once, you are done. So to do this in a soft SVM, let's do the hard SVM first. We just had alpha greater than 0. So what will happen? Can a hard SVM solve this problem? Does anyone have an answer? So if this term goes to 0, so maximum of alpha transpose 1, where can it go to for alpha greater than 0? Where it can go to? This is unbounded, right? So if you want to maximize x such that x greater than 0, what is the value of that? What is the value of x such that it maximizes? Somebody? What is the maximum of x such that x is greater than 0?
Infinity, no?
Correct. so it's infinity. So here also it will tend to infinity. Can the SVM solve this question? So for a particular alpha, when this goes to 0, this will make the alpha infinity. So the SVM will not learn anything. It will learn some perpendicular lines. So it will not learn anything important. But here comes the importance of soft classifier. In soft classifier, you have a bound. So in this case, alpha will be set to C. Here this will go to 0, but alpha will be set to C. Did you understand? So in a large setting, what we just skipped is only one thing, that is this derivation. So this derivation is trivial, it's just algebra when we derive this line. So I showed you how to derive the Lagrangian, take the derivatives, remove x and get it in terms of alpha. So this is the algorithm of SVM that I've written down. So you can clearly see from here, once you have found alpha, so you can clearly see W can be written as summation of W1 to n alpha n yn xn. Once yn and xn are known, alpha if you find, you can find this. And B, how can you find? If alpha n is greater than 0, there is one condition in KKT conditions which says that if alpha is greater than 0, hi has to be equal to 0, which means that this is a alpha n means n is a support vector, or W transpose xn plus b into yn is equal to 1. If alpha n is 0, means the constraint is greater than 0, means the corresponding constraint must be equal to 0. That's what you must understand. So that these are the support vectors. From here you can easily find b. How? Multiply both sides by yn. So yn, if you multiply both sides, what will you get? So yn, if minus 1 into minus 1 is equal to 1, 1 into my 1 is also 1. So you will just remove yn here. So yn square you can clearly see is equal to 1, because they are either plus 1 or minus 1. So you will get W transpose xn plus b is equal to yn. So b can be written as yn minus W transpose xn for alpha n greater than 0. So is the idea clear, or I'll explain this idea clearly before I go to coding, or else I'll go to the coding. I think there's a problem here. There's a KKT condition says that these Lagrangian into the constraint functions must be always equal to 0. So if a Lagrangian is greater than 0, if a multiplier is greater than 0, it means the constraint has to be equal to 0, which means this is a support vector. So whenever you have, so remember this, whenever you, people can ask this. So whenever you have alpha n greater than 0, these implies to support vectors. So if you have a doubt, to ask now, or we'll go to coding, because we'll be using this algorithm itself to code SVMs. So this is the entire idea of an SVM. We did not, ideally we need a lot of more time to cover it, but I just wanted to give you the big picture of it, how you want to separate the classes far away. So there are also other ways to do non-linearity and stuff, so we'll not go to that. But we want to separate these classes as far as possible, which a logistic regression cannot. So is the big picture idea clear? And if you have a question regarding a particular thing regarding this algorithm, you ask now. Otherwise, in the last 5 to 10 minutes, we'll be doing the programming.
Maina.
Yeah.
Actually, SVM is supposed to be outdated when in 2001 random forest came into the picture. Why it happened? What do you think?
SVM is not that outdated. Random forests and SVMs, I think, perform equivalently when you see papers and all. They don't get outdated. Random forests are, these things will be doing a variant of random forest later. So random forests are sort of decision trees. What you do. So
right.
there you, So in that case, I don't think they are sort of outdated. They are outdated after you have gone, because SVMs can solve linear regressions also. It does not only solve logistic regression, you can also solve linear regressions here. So random forests are sort of they have seemed to perform well compared to SVM, almost equal to SVM, but SVM is very robust. So I think SVM is much stronger, right? Because when we derive the decision trees and all, we have shown that decision trees have a lot of problem in building, learning. You have to know all these entropy functions and all. You must remember the second lesson, that tutorial that we did. But in case of SVM, it's very simple optimization problem. I don't think this is a correct statement that SVMs were outdated when in 2001 random forest came.
If you see this comparison on the net now, or
Yeah.
if you Google it now, you will it is obvious by reading that the SVM is not preferred over the random forest. So random forest is preferred over the SVM because random forest has always have the good performance and good accuracy. That's why I'm making this statement, and I'm pretty sure that this is the confirmed statement is available.
Okay, I think I have done a few. I have seen a lot of papers where random forest and SVMs perform equivalently. But yeah, like SVMs, there is something you need to do about the kernel also. Random forests are, maybe you can have some non-linear decision boundaries, wherein SVM you have to. This is possible. Like random forests, you can have all these non-linearities between this point and this point. You consider these things. For between there's this other 2 points, you can have considering other things. But in SVM, generally you need to choose a kernel for that we have not done in this case here. So if you have a kernel that you want to choose, the kernel will decide your non-linearity. You can see here that W transpose, these two terms are here. So instead of this, people what to do, people take a kernel here to represent non-linearity between data. So for example,
selecting the proper kernel is a big problem now here.
Yeah, that is a problem, but I think SVM is very elegant. But like maybe performance wise, a random forest may do well, but the SVM is the best algorithm that people understand. Like from a machine learning perspective, see, isn't this very elegant? You are just trying to minimize the distance between the endpoints of a road, and you are getting an entire algorithm. There is nothing like big mathematics here. So that's the reason people. Yeah.
Please go ahead. Sorry.
No, you are saying something. So I was saying the kernel is difficult.
What are the use cases of the SVM? That was I was about to ask now.
SVMs are used everywhere. So if you go through some papers, the papers and works that I have done, so what you do is you set a baseline by using a SVM. So random forests would generally not be able to do. So if you have some structured data, random forest is good. For unstructured data like speech and all these things, SVM will perform much better. In that case, if you have a proper kernel, generally a Gaussian kernel of this form, x1 minus x2, does very well. So in that case, SVMs are easy to interpret and all. Yeah, I think I have shared my. Yeah, so if you have a doubt, you can ask. So this is.
What is the best application of this SVM?
So any logistic, any problem where you're trying to do classification is a very good application. So you can set this as, so somebody has asked a question, we'll just answer that and then come back to you.
So for classification problem, it is best suited, you mean to say?
No, not even best suited, but it is like a sort of a trademark. Even in large complex models like GANs and all, what people do is they use an SVM to set a baseline. So you want to set a baseline, so your neural network must perform better than SVM. So this is what presently SVM is used for. But previously SVM was the first robust classifier, since I showed you that it was finding this large margins between these 2 points. This was one of the first very, very sophisticated classifiers people came up with. And a very important thing about SVM is it is interpretable, very nice interpretable. I'll show you in this program. I'll be doing a use case just now, a classification problem, then it will be, I think, very clear to you.
So it is very good for unstructured data, you mean to say, right?
Yeah, it's very good. Like you cannot do stuff for unstructured data in random forest that well. Like in audio, like data, if you want to find languages and all, random forests generally do worse than SVMs. Structured data, you can see decision trees does well, but SVMs, like I think, it is very elegant. It does not depend upon the type of data that you are trying to feed to the system.
As compared to neural networks, you will prefer neural networks over SVM.
That is true, because that's why you use SVM as the baseline to determine how the neural network is performing. So you must always perform better than an SVM when you're doing neural network. That's the idea. Because
thank you.
Yeah. So if you
Is
have a
it-
question, yeah.
Is it suffering from overfitting?
SVM, that's the base thing, right? So I wanted to show this thing that I'll show it in the programming thing. So can you observe this thing? And this is a very good question. SVM cannot suffer from overfitting. So that is the biggest point. It can if you select C accordingly. So does this equation seem familiar to you? So I wanted to, so Andrew NG has this interpretation of SVMs where he says that this C term, right? If you just subtract, if you divide this C somewhere like this, so what will happen is 1 by 2C plus, right? This is what you will have. This is sort of the loss, and this is sort of the regularization, right? That we did in a linear regression. Did you remember, Professor?
Right.
Yes.
Right.
So this interpretation is very nice. So SVM people did not have this interpretation initially, but when you divide C by this, you clearly see that it turns out to be a regularization. Inherently, the margin, setting a large margin is making you regularize. It does not change. So it cannot suffer from overfitting. If you choose very high values of C, then it can suffer from overfitting. Is this?
Thank you.
Then this term, yeah. So let's go to the coding in the last 5-10 minutes. So sorry if I rushed through. I wanted to do it in much more detail, but 1 hour, and if I'm overshooting by 20-30 minutes, in that case
It's okay. It's okay for us.
Yeah.
To learn the different things, we need to do this also.
So yeah, so let us do the coding now. Yeah, hello. Now, can you see my screen?
Now we can see.
Okay. So I think we have once spoken about this. I'll take a simple data set and show you how SVM is good. So this ideas data set is what I'm using again. Next day we'll be using some complex data sets. So this ideas data sets I had used in the linear regression, and I had used in some like a naive classifier also in the first tutorial. So let's import these libraries. So I'll just use a complex optimization library because it's a convex optimization problem that we are going to generate. Other than that, we're not going to use any library. So here I'm just loading the data. There's nothing to explain here. So I loaded the data. Generally, I'm using 2 variables here. You can use all the variables, but for showing the results in a systematic fashion, I'm using only these 2 variables. So these 2 features, petal length and sepal length. So that's what I have taken. I've taken 2 classes, that is the Virginica class and the versicolor class. There's a reason why I'm taking these 2 classes. This is basically this. They are overlapping.
There are actually 4 classes, no, in this data set.
3 classes. We have Virginica, versicolor, and setosa. In the first class, we had done with setosa. The setosa is far away. So I'll show you if you want to see. This is these 2 classes. If I set it to 0, you can see how far away they are. This is the reason I'm not taking this. This is a trivial problem, right? Everybody can learn. Even a naive classifier can learn. Do you understand why I'm taking the difficult problem?
Yes. Would you share the link of this?
Yeah, everything will be shared. I have shared the Google Drive link. Everything will be there in the chat. And also,
Would you share? Please share this in the chat box.
I have already shared it. Okay, I'll share it again. This is these 2. This is there is overlapping. So we'll be needing some soft SVM, right? So I told you we will need some slag variables to account for the shift between -1. So away from -1, there is some shift. So I'll just show you. See, the SVM code is so small, so nicely written, so nice algorithm that you can just write it in 2-3 lines. So what you do is, as I told you, so I am taking y as a diagonal vector. So y is this is the label vector, so containing +1 and -1. Label containing +1, -1. So I'm taking this as a diagonal, and I have shown you how I made x tilde by multiplying y into x. So I showed you. So we generated the gram matrix something like this, right? So recall. Gram matrix was something like x transpose. So x tilde, to be precise, x tilde, x transpose, by x tilde we were accounting for the values of y as well. So that's what I've done. So x tilde I have taken as y into x. So if you multiply a diagonal matrix with x, so you actually multiplying each row with the y corresponding y. Now you see this cvxpy, this thing, cvxpy is a very nice sort of a classifier. This is a library that you can use for a convex optimization problem. So what I am doing is I am setting a parameter here. So the g parameter I am setting the value to be, this is the constant value of x tilde that I had defined, right? And I have said that PSD equal to 0 means if it is positive semi-definite, 0 eigenvalues are allowed. So if you set it to 0, this will give you some errors. False if you set it to, this will give you some errors, so you need to set it to true to account for allowing 0 eigenvalues. So this is what the value is. This is the Gram matrix that I have defined. So x tilde, as I have defined. So and one hot vector I have defined it according to the shape of y, also the shape of alpha. And alpha is the term that you want, right? So alpha is a dual term that you want to find. So and then I have written the loss. See the loss function. So this is the optimizer. The optimizer I have imported here. cvxpy is an optimizer. Somebody is, can you mute yourself?
Vijay Nathan, please mute yourself.
Yeah, please, Professor Vijay. Yeah. Okay. So the thing is, this one hot vector, as I defined, alpha times 1, alpha transpose 1 is also 1 transpose alpha because it's a scalar, and this quadratic. This means this is a function which says that a quad form is of the form x transpose gx. This is what I'm writing here, or here alpha to be precise. So I'm defining the optimization problem here, and then I'm optimizing over this. I'm trying to find the maxima here. This is the maximum. So maximizing over this with the constraint that alpha is less than c that I told you. These alphas are bounded. This is sort of a regularization that you're trying to do, and alphas are greater than 0, such that alpha transpose y, you can see the algebra that you will have another constant, that is alpha transpose y equal to 0. You have all the notes there. So it's just derivative and setting to 0, you will get this constraint also. So now if you develop this optimization problem, this library will solve it. So we're not going to solve, this is not an optimization class, so we'll not solve the optimization problem. This constraint of this is a equality optimization problem, you can do it, but this is not in the scope of this class. So optimization problem dot solve. So this is the library will solve this. There's a solver of cvxpy, and now you have the value of alpha in alpha. Alpha knows the value, optimal value. So now you set w as x tilde alpha, and b as I was saying, if alpha is a support vector, this sets the support vector. So you can clearly see, and
we are not creating any object of this SVM here.
Yeah, we are all SVM. We are not only doing only. I told you now. I'm coding SVM from scratch. This is the SVM object.
Okay, so you are not using ready-made library function of SVM.
That is the thing. I'm just coding. I'm just doing it from scratch. So you can see this is alpha transpose 1 minus half g alpha. So it's optimizer only will optimize this function. That's it. There's no more library we are using. That's the thing I wanted to. That's why I showed the entire derivation of this function that made it an easy optimization problem. The initial problem would not have been done this way. Is that okay? So you have see alpha transpose 1 minus g half alpha g transpose. This is the optimization problem that we had, and we just set those constraints in the cvxpy, and the cvxpy will give you the alpha. There is no SVM inbuilt model that I'm using. That's the upside of this tutorial that I wanted to portray. So you wanted to alpha, no, not a single lesson we are doing is going to use any library functions. Library you can always use, but you will not understand. So here you can see these are support vectors. These are the support vectors. Vectors where alpha n is greater than 0 and it's less than c. So these define the support vectors. So you found the support vector, and as I told you, it's y minus w transpose xb. That's what I have done. Found this value, yw minus y transpose xb. This is the value of b. So as we had done previously. So this is the SVM function. This will return w and b. So I have set a regularization term of 1, which means that I do not give. I give a larger weight compared to, so I'll show you. So see, it has learned so fast. So I'll show you, I'll display this. This is nothing but display. Just see now. So these are the margins. So if I do something like increasing the C, so can you tell me if I increase C, what am I actually doing? I am making the slag variables, finalizing the slag variables, right? I'm not, if you have slag variables, you want to have smaller slag variables. We're actually decreasing regularization, right?
Yes.
Yes. So 1 over C, that term I showed you, decreasing regularization. So this margin will become smaller. See, the margin became smaller, and the number of points that were inside has also reduced. So similarly, if I use a very small C, for example this, so it will be highly regularized. So see, it does not learn anything proper. So you need to select this C value, ideally between 1 and 5 is doing well here. So this 10 also will do. So you see, even smaller margin. So this is less regularization. More regularization you do, these margins will be larger. Is that okay?
Yes.
Yeah. So this was the code. I've shared the code. You can use this. I think this will be much faster than the SVM import inbuilt library. So this is a general code you can use everywhere. So anyways, so if you have a question you can ask, or I'll be sharing the things that you wanted. That is, I'll just reshare these. Copy link. Okay, I've shared these two. I'm also sharing my email ID as somebody has asked. That's all. If you have a question you can ask, or we will end it for today and see you next week. Okay, it doesn't seem that anybody has a question. Hope you enjoyed today's session. Bye.